on mathematical aspects of scattering amplitudes. And yeah, we are already very curious to learn more about Lambda varieties and monotony. So please go ahead.
Okay, so I got to stick to my proposed schedule from yesterday. Very good. So in this recording session, we don't have any live musicians, I'm afraid. But so what do? We have very little time. But anyway, let me try to begin with a recap of a couple of things I talked about in the first two lectures, just to remind you and to put everything into context. So we started with Feynman integrals. And there's many different ways to think about them and to write them down. So a common starting point is in momentum space, where you have an integral over loop momenta. So the number of loops depends on the order and perturbation theory that you're at. And then you have an integral over Minkowski space of these loop momenta Lk. And then the integrand is a rational function, actually. So it's just an inverse of a product of quadratic expressions raised to some powers. So these QEs, I mean, they could, for example, be things like mass of an edge squared minus momentum flowing through an edge squared, something like that. And then what we did, I explained roughly how the Schwinger parameters or Feynman parameters, the end result is the same, how you can introduce these parameters and do all the loop integrals. And then what you're left with is an expression that has some little gamma function. And now what previously were these factors, these denominators QE, for each of those you now have an integration over a parameter, which is this Schwinger parameter. And they're raised to these indices in the exponent. So this is the integration measure, so to say. I mean, essentially, this is some kind of Mellon transform. It's a standard integral transform. So the meaty part, what distinguishes the different graphs and integrals, is what is the thing that comes after this. And this is determined by two polynomials, these graph polynomials, and they're raised to certain powers. So these things here, we talked about those. So this is like a graph polynomials. You can write them in terms of spanning trees, or spanning two forests. So this is something combinatorial of a graph, which is quite neat and useful sometimes. Then in the numerator, you have this delta function, so you can actually do one of these integrals and simplify the integral. I mean, which age you choose depends on your approach and what you want to achieve. So you have a lot of freedom there. So this is the parametric integral representation. And maybe let me just do an example to make sure this is absolutely clear what that is. So let me look at this triangle integral. I don't think we had that yet. So we have just one loop. We have three external momenta, P1, 2, and 3. And let me give labels to the edges. So I label these edges 1, 2, and 3. And note that once you're using this formula, you don't have to worry about momentum flow. So you don't have to choose L's and L plus P's or whatever and write them on the edges. So at that stage, this is all taken care of already. So you just have to label them. And for definiteness, let me say we're in 4 minus 2 epsilon dimensions, and we set all these indices equal to 1. And let me also set the masses to 0. This is a very special case, but actually this is a kind of integral that does play a role. So these things do show up in calculations. Now, what is the U polynomial? So this is a sum over spanning trees. So let me just tell you what it is. It's x1 plus x2 plus x3. And if you want to know what the spanning tree is, so if there's one spanning tree which consists of the edges 2 and 3, right? This connects all the vertices, but you're missing this one edge. This is the edge 1 that you're missing, and this is why you get this x1. So and there's two other spanning trees. So you have this one where you're missing the edge 2, and you have the one where you're missing the edge 3. So these are the spanning trees. And then the other polynomial, which has the kinematics in it, f, So this has the following form. So this is now quadratic in the axis and linear in the squared momenta. And of course, it's very symmetric. So with the labels that I've chosen, you get this expression. And now the combinatorial interpretation with these two forests. So how do you get this P1 squared x2, x3? So you're missing the edges 2 and 3, right? So actually, you only keep the edge 1. And then the vertex where P1 comes in is left over, and you have deleted these two edges. So this is a forest of two trees, two very small trees. And this gives you this term. And then here, I believe it's the one where you only keep 2. And here you have the two trees where you only keep 3. Okay, so these are the two forests. So just to make this concrete, right? So this is how this looks like in an actual example. And then now if you want to write down the integral, okay, how do you do this then? So first we have to work out this power counting degree, this of convergence. So in this case, these are the ends, and they're all 1, and you have 1 loop times half the dimension. Half the dimension is 2 minus epsilon. So the whole thing is just 1 plus epsilon. And now if you use all this and you use this projective formula, you can write down the integral. And here I use the convention. Let's say I use this delta function to put x3 to 1. Then this is just 1 plus epsilon, gamma 1 plus epsilon as a prefactor. And then you only have 2 integrals. One was fixed by this delta function. And then because the indices are 1, you simply just get dx1, dx2 over uf. And then if you work out these exponents here, you can rewrite it slightly and put all the epsilon dependence in this form. Right, and everywhere here, I set x3 to 1 in these polynomials. So this is an integral representation, and in this case, this is actually convergent. So this is convergent, even when you set epsilon to 0. And that means you can expand under the integral sign. So you get the epsilon expansion from a very simple procedure. So this is what is often useful in practice to compute these integrals in an epsilon expansion. So how would you do this in this case? Well, you have to expand this this gamma function epsilon. This you can look up. This is a very well-studied function. There is an explicit formula as a series in epsilon. So you can write it as an exponential. And then in the exponent, you have this explicit power series that I'm writing down. So it has a constant here, the Euler-Mascheroni constant. And there's some Riemann zeta values starting at zeta 2. And then some powers of epsilon. So this is just gamma of 1 plus epsilon. So of course, the exponential is easy to expand. So any term in the epsilon expansion to arbitrary order, you can easily get this from this formula. And now you have this integral to expand, but because it's convergent, you can just work with this integrand here, right? So you can write this as e to the epsilon times the logarithm of the ratio of these u squared f. And then you just use the power series for the exponential, and you can write this as a sum. And because this is convergent, you can actually commute the sum and the integral and put the power series from the exponential in front, and you're left with an integral that is now independent of epsilon. So in here, you just have dx1, dx2. You have uf. And then you have this logarithm to some power. Okay. So the point about this is that this thing here, this is a convergent integral. Is independent of epsilon. So if you want to compute a term in the epsilon expansion, you can use this and then write this coefficient in the epsilon expansion in terms of these kinds of integrals. And these are well-defined integrals, so you can evaluate them numerically with many different methods, or you can try to compute them exactly with symbolic methods, maybe with polylogarithms sometimes. I mean, doesn't matter. So the point is that this gives you a convergent integral representation of this epsilon expansion. Okay, so that was an example where things where life is easy because everything converges. Now, in general, this is not the case, and we talked about what you do when you have divergences. So the idea was, sorry, this here. There are divergences of these integrals, and they come on hyperplanes. So the location of these divergences are given by linear equations. And they have this form. So omega is some power counting degree that are defined. And whenever this is 0 or -1 or -2, you have poles. So this was the power counting thing. And there is a geometry behind this, right? There was Newton polytopes and convex geometry to describe this. And the idea was here, you look at the integrand under a scaling. So when you rescale the Schwinger parameters by certain powers, and then you look at what happens when rho becomes very small. And this power counting was this exponent exactly, and you have higher orders. But the higher orders don't matter for the question whether there's a pole or not. Okay, and so this power counting analysis, this is sometimes also called, I mean, it's closely related to sector decomposition. So I drew a picture of the sectors for the bubble integral last time, where the scaling is different in different regions. And there is another technique where this is used, which is called expansion by regions. So I'm not going to talk about this. I'm just mentioning this in case you know it. So this is also something where this generalized power counting is very useful. Okay, so we have these divergences, and then we discussed, well, okay, there are divergences, but you can actually go beyond them. So we talked about the analytic continuation. So the idea was integrate by parts, right? So this does not change the integral, but it gives you a different integral representation. So if you integrate by parts in a smart way, you can increase the domain of convergence. And we did this example for the gamma function, but the thing is this generalizes. So if you have an arbitrary subdivergence in your Feynman integral and you go to the scaling coordinate, then by definition, the integrand looks something like this. So the overall power for small rho is something like rho to the omega. And f is whatever's left over after we factor off these powers of rho. So f is something that is regular at 0. And then we discussed there is this integration by parts, a procedure, very simple, which means that you can pull out certain prefactors that give you explicitly the location of the pole. So they come out of the integral, these singularities. And what's left over after k plus 1 of these integration by parts is an integral where now the behavior at small rho is much improved. So you can improve it as much as you want. So you can also make the integrand vanish very quickly if you want. So this can be useful for numerics, for example. But mainly the point I want to make is that you can use these integration by parts to make the integral eventually convergent. So if you do this, these integration by parts in all of the regions, all of these sectors where you have divergences, ultimately things will become finite. And so this proves eventually that you have this meromorphic continuation with simple poles. And this means you get an epsilon expansion So you also can write down formulas for the terms in the epsilon expansion, also for integrals with on a pole. Yeah. Okay, and then the final thing I mentioned at the end was, okay, that we now have these, we now know where the epsilon expansion comes from, that it exists, and how to compute it. And there was one more interesting thing. There's this factorization. So when you're on a residue, something funny happens. So first of all, on the residue, the integral simplifies, and no anything else. And it not just simplifies, it simplifies in terms of other Feynman integrals. So if you do the scaling, for example, and you look at this U polynomial, then to leading order in the scaling, it's a product of the sub and quotient graph polynomials. And this means that the residues factor. So this meant that residues factor into sub and quotient graph integrals. And when you think a bit about what this means, this is super important, and you know this under different names. So this is very closely related to renormalizability. So the fact that the subdivergences actually come from lower loop order graphs. So the idea is once you renormalize those, then the subdivergences are all gone already. Liability. And also it means that you have like a graph by graph a renormalization group equation or theory. Right? Because it's not just that overall for a correlation function or Green's function, you have this relation of the higher order poles, but for every single graph individually, you can relate the higher order poles of it to its sub and quotient graphs. And the formalization of this leads eventually to what's known as the Hopf algebra of Feynman graphs. But unfortunately, I don't have time to talk about this. But all of this rich structure, it really comes from this factorization. So this is really a key property, this factorization on residues. Okay, so I think so much for the recap of what happens in the dimension and these regulator variables. Now we want to go to a new domain. So let's have a cut here, and let's review what did we actually do. So we looked at a Feynman integral that depends on the dimension, the indices, and the kinematics. Right. So this was masses and momenta. And so far we only looked at the dependence on these things. So this is first of all, you notice these things are single valued. Right? So there's no question of what the coefficients are in the epsilon expansion or what the function is. It has a unique value everywhere away from the poles, of course. And so it's single valued. And its singularities are therefore they're only meromorphic. This is something we understood. Now, when you look at the dependence on the kinematics, it's very different. The thing is multi-valued. So you have to be very careful with branches of functions and so on, and the correct I epsilons. So there are things like logarithms, which are defined only up to 2 pi I. There are square roots, which can have different signs, and similar things. So this is very different, a very big difference. Then the singularities themselves, they are on hyperplanes. So I just reviewed, right? So they are given by linear equations. And maybe you remember there was this example I did, this bubble graph, where I drew the poles and the region of convergence. And it had this, this shape. There was like 3 families of poles that started at some point. And there was a vertical family of poles. And they keep repeating forever. And there was a horizontal family of poles. Right, so you notice, and this was the region of convergence, this triangle here. So everything is linear and it repeats infinitely many times. Now, what does the divergences, the singularities in the Zs look like? So these are called Lambda varieties. And those can be very different. So I'll do an example later. So now the variables that I draw are the kinematics. So let's say I draw the masses normalized by the momenta. This is just so I can draw a 2-dimensional picture of a 3-dimensional thing. And for example, you could have things, there can be linear components as well. So you can have singularities when some masses vanish, for example. So you can have these coordinate axes. But you can also have nonlinear things. And there's only finitely many. So the differences are these singularities are can be nonlinear. And they don't repeat. So I mean there's only finitely many. Whereas the poles here, there's infinitely many of them. So that's another big difference. Then how did we actually get the singularities, right? How did we figure this out? This was simple power counting. And remember, there was this Newton polytope business. So there is a geometric picture behind what's going on. That's pretty simple, actually. Now, on the other side, how do you figure out the singularities in the kinematics? So there's something called Landau analysis. I mean, there's different kinds of Landau analysis, but it's a different procedure. It's much more complicated. This is easy. This is complicated. Yeah. And then finally, here, because we have these poles, right, we can talk about residues. Now, if on the other hand, it doesn't really make sense so much to talk about residues because the singularities are of a different type, right? You have these logarithms and square roots and whatnot. But somehow what's more interesting here is the monodromy. So how does a function change under an analytic continuation when you go back to the original point? So this is also sometimes called discontinuities. Across a cut. So maybe that's a language you're more familiar with. When I say monodromy, I mean the same kind of things. And then there's an aspect that I don't have time to talk about. Unfortunately, there is difference equations in the dimension and the indices. So you can relate the integrals with different indices. And on the kinematic side, sorry, I got my color coding wrong. This should all be red. There are differential equations. And these are super useful to compute integrals, for example. But I don't have time to talk about them, unfortunately. So maybe let me just give you one kind of hint on these last 2 points. So for example, let's look at this integral. I had it at some point as an example in the previous lectures. So this is like 2 loops, no masses. Pretty important integral for renormalization group calculations, for example. Now this thing, right, this depends on This depends on 5 indices. It has 5 edges. Okay, I mean, it also depends on the dimension and momentum, but I don't want to focus on those. And now recall maybe what is like the simplest difference equation. We looked at the gamma function, right? And for the gamma function, you can write gamma n plus 1 is n times gamma of n. Right? Actually, we proved this in the last lecture. So here you have an instance, right, where when you shift the index by 1, you actually get the same function up to a little rational prefactor. And these difference equations are generalizations of these to Feynman integrals. Now, it doesn't work as simple as that. So the problem is when you shift, you cannot always express it just as a multiple of the unshifted function. And you have to have several things on the right-hand side. So in this case, for this particular example, you can try to do the following. So let's say we shift the first index by some integer k1, shift the second by some integer, the third and the fourth, so on and so on. So let's say we look at all of these shifts, right? Then no matter what integers you choose, then you can always write this as a linear combination, some coefficient that depends on n and k times the unshifted integral. And then another coefficient that also depends on n and k times the integral where, say, you shift the first one times a third term where you shift another one. I think the last one works. I mean, so this is one possible choice, and that's it. So it means no matter what shifts to choose, you can always write all of these shifted terms as a linear combination of these 3 with some rational prefactors. These are rational functions of the n's for each k. So these are not rational functions in k. And for different k, these functions become much more complicated. But for fixed k, these are rational functions in the n. So this is the kind of difference equation. So again, it's a linear combination of integrals with different shifts. So it's a generalization of this type of equation where you have several terms on the right-hand side. And these are super useful in applications, and I'm sure many of you have come across those. So in this case, you would say there are 3 master integrals. But this is a terrible terminology because it means different things to different people. So maybe forget about it. Anyway, I don't want to talk about this. I don't have time. I would like to, but anyway. So, and similarly for a differential equation, you take a differential, say to some mass or whatever, integral. And you can write it as some linear combination, some finite number of terms, 1 to r, some rational coefficient times one of your basis integrals. So similar like this, just on the left-hand side, you don't take another shift, but you take some differential. Now the right-hand side looks similar to the right-hand side here. Okay, so we've seen this these different worlds, and now we want to, in the last 1.5 lectures, I just want to talk a little bit about these points. So how do you figure out what the singularities and the kinematics are? And maybe mention how you can, in principle, at least think about where these monotonies come from and how to compute them. So this is what I'm going to focus on for the rest of these lectures. Okay. So let's do an example. Pretty much the simplest example I could think of. So this is now dependence on masses and momenta. Okay, so let's take the following example. Let's take the bubble graph, but this time with full kinematics. So there's a momentum running through, and we have two masses, M1 and M2. Okay, let's take the completely this one loop graph. But for definiteness, I'll just consider it in 2 dimensions, which is convenient because then the thing is finite. You could do it in 4. It wouldn't really change the geometry of the analysis, so the outcome for the singularities would be the same. But this way, we don't have to worry about the analytic continuation in the dimension and the indices. So let's just take it in 2 dimensions, and then this integral. And so now I fixed the dimension and the indices, so I will not write them. I'm only looking now at the dependence on z. So this is now a vector of 3 coordinates. So there's m1 squared, there's m2 squared, and there's p squared. So this is our z. And if you work out what happens in this case, so again I take the projective form. This time I use x1 plus x2 as the delta function. Because this only has 2 edges, and I use the projective form where one integral is already done, you're only left with a single integral from 0 to 1 in this case, if you work out how the delta distribution works in this case. It turns out it's just a single integral of dx over f, where f is the second semantic polynomial, the second graph polynomial. So the first graph polynomial actually doesn't play a role in this case. So in this f, so if you can write it down, it's x times m1 squared plus 1 minus x times m2 squared minus p squared x times 1 minus x. So this is a quadratic polynomial. And that's it. You're just integrating dx over this quadratic polynomial. So because it's quadratic, I mean, in principle, you could compute its roots if you wanted to. But of course, it will be a bit nasty. There will be some roots involved. So let's not do that. But it has 2 zeros, this polynomial. S1, let me call S1 and S2 the zeros of this polynomial. And then how does the geometry of this integral look like? So when you look at the x plane, right, there is somewhere there's 0 and somewhere there's 1, and you're integrating from 0 to 1, right? This is your integration domain, the interval. And then somewhere, depending on what the actual values of the masses and momenta are, you have S1, and somewhere else you have S2. So you have these 2 zeros of the denominator that are somewhere in the x-plane. And now the question is, how does the integral depend on z, right? So when you vary z, you move around the masses and the momentum. But what happens is that these points, S1 and S2, move. Right? So they move around. But as long as they stay away from the blue line, of course, nothing dangerous happens, right? The integral is bounded if it's far from the blue line. So you know immediately that this integral Iz is smooth. It's smooth, and actually it's also holomorphic. It's smooth and holomorphic. As long as these 2 points, these singularities, don't hit this integration path from 0 to 1. Now, what happens when you're hitting the integration path? Right, you may be worried that the integral becomes singular, right? Because if you're integrating very close to the singular point, then the integrand is unbounded and becomes infinite. So the integral would seem to blow up in this case, right? So let's consider a case where, okay, you're integrating from 0 to 1, and maybe you've changed the masses and momenta such that S1 is now very close to the integration path, and you want to move it even closer. Then the question is, what happens to the integral? Now the observation is that actually it's not a problem, because the integrand, right, this form dx over f, actually this is holomorphic in X. And because this is holomorphic, you can apply Cauchy's theorem. So you can deform the contour without changing the integral. So if you're computing the integral at a position where the S1 is very close to the blue line like this, you know that actually the integral is the same. So I'm in the same configuration, right? So I have 0 and 1, and I have this S1, which is very close from above to the real line. But the integral stays the same even if you move the integration path like this. So the integral over this path gives exactly the same integral. And this means, okay, well now there's no problem, right? If S1 goes down, then the integral stays smooth and holomorphic, even if you're now at this point where S1 is down there, because you can just deform the contour away from S1. So actually, this means you have an analytic continuation, right? So this means that this integral Iz has an analytic continuation even when the singularities cross the line, the interval between 0 and 1. The function stays, if you change this integration path like this, the function stays analytic. Okay. So you can do this analytic continuation in this way, but it doesn't always work. There's obstacles, and this is what then gives you the Lambda variety. So far we haven't seen any singularities of the integral, because you could always move away. So the real singularities actually come when you cannot move away. So there's different scenarios how this can go wrong. So this contour deformation fails only in the following cases. So the first case is well, what happens when one of these singularities goes to 0? Right? Remember, 0 is the point where your path starts. So if so say Si goes to 0. Now the problem is the path starts in 0, right? So you can deform it, but it will always start in 0. So the problem, you cannot move its starting point away from 0. The start and end point are fixed. If you remember Cauchy's theorem, I mean, you are allowed to deform the path, but you have to keep the end point fixed. So that's why you have a problem here. So then you cannot deform, and indeed you would expect to get a singularity. At least there's no reason why there couldn't be a singularity in this configuration. Now, when does this happen? Okay, you want that one of the zeros of f is at 0, right? So this is exactly the case when 0 is equal to f of 0. And when you look back up what f was, this is exactly m2 squared. So when the mass 2 becomes 0, you have the situation that the one of the singularities coincides with the starting point of the integral. Now there's an equivalent picture. What happens when one of the points goes to 1? Well, this is the mirrored situation. So now it's just the other endpoint. And if one of the singularities goes there, again, you're stuck. You cannot deform the contour. Now, this is when f of 1 vanishes, which is m1 squared. And these two scenarios, they're both called endpoint singularities. For the obvious reason that I explained. And then there's the third configuration, number 3. So this is when S and S2 become the same, right? So in general, this quadratic polynomial will have two different solutions, but maybe you're unlucky and actually it's a double solution. Maybe the polynomial is a complete square and you don't have two different points, but it's like a point with multiplicity 2. So how does the situation look? Well, you have your integration path from 0 to 1. And now you can assume that you're not at 0 or 1. So that's not the problem. So let's say S1 is here and S2 is below. But now suppose they become the same. And then the problem is that they pinch the integration path between them. So you cannot wiggle the path out of there, right? You are only allowed by Cauchy to deform the path smoothly. So you cannot take the path around the singularity, right? Because then you would pick up a residue contribution. So if you have to stick between S1 and S2, and now S1 and S2 become the same, you have no way to avoid getting arbitrarily close to the singularities. So this is a pinch singularity. And you can convince yourself that these are really the only situations that can cause a divergence of the integral that you cannot avoid. Now, how do you characterize this? This is described by what's called the discriminant. So whenever you have a polynomial, whatever degree, there is another polynomial associated to it, which is called the discriminant, which vanishes exactly when f has a repeated 0. So how do you do this? I mean, you all know this very well, of course. This is a quadratic polynomial, so let me just write it out. So if you expand it in x, it has this form, p squared x squared. If you collect all the linear terms, you get m1 squared minus m2 squared minus p squared. And then you have a constant term, right? And if you call this a and b and c, right, then you know that if you compute the zeros, right, so S12 is something like minus b over 2 plus minus square root b squared minus 4ac over 2. So they are the same exactly when this argument of the square root vanishes, right? So this is the discriminant. This discriminant for a quadratic polynomial is b squared minus 4ac. Yeah, and you can work out what it is. I mean, it's written there, right? Okay, so what we realized is that whenever this combination of masses and momenta is 0, then you have this pinch situation, which could cause a singularity of the integral. Now, if you find this a bit unusual, or what is this supposed to be, then as a little exercise, you can show that actually you can factorize this. If you take roots of the masses, you can write this as p squared minus the sum of the masses squared times p squared minus the difference of the masses squared. So now your physics intuition might agree, right? So you see there is a potential singularity when p squared equals the sum of the masses, and there's a singularity when p squared equals the difference of the masses. So this would be called the normal threshold. And I think that this here is called the anomalous threshold. So these are all things that you would expect if you have experience with these singularities, of course. But I hope this simple geometric picture explains where this comes from. And then you define, in general, this Landau variety that I mentioned earlier. So the Landau variety of an integral is the smallest subset of defined a subset of the kinematics subset in kinematic space so this is Z space, masses and momenta. So the smallest subset in the kinematic space defined by polynomials such that away from this set the function has an analytic continuation. I of Z has multi-valued. I mean, in general, these will be multi-valued, as I mentioned earlier. So when I say it has an analytic continuation, I do not require that it is unique, like we saw it was for the dimension and the indices in the first two lectures. So in general, it will be multi-valued, but still, there can be analytic continuations. In the entire domain away from the Landau variety. So let me call it L. Yeah. So what is it? So it's a subset in the kinematic space where the singularities are. So that means if you're away from L, you can always avoid the singularities and you have an analytic continuation. So just to finish the example, and then we take a break before the final lecture. So in our example, in this example with the two masses bubble, right there the Landau variety is defined by, so it's a subset that is defined by, you have singularities when m1 squared is 0, or when m2 squared is 0, right? These are the endpoint singularities. And you also have a singularity from this discriminant. Right, so this was the endpoints. And this was the pinch. And now if you draw this in a picture, you get this thing that I showed earlier. Right, so this is a subset in 3 variables, but everything is homogeneous in the masses and the momenta. So I don't lose any information if I just scale everything by p squared. So this is why I drew this diagram with the axes m2 squared and p squared. Right, and then you have these 3 components. So you have singularities here on the vertical axis. You have a singularity on the horizontal axis. And then if you work out what this is, right? I mean, it was a polynomial in the masses and momenta. And if you write it in terms of m1 squared and m2 squared, it's a hyperbola. So I think there is some intersection points here. So it looks like something like this. Okay, so in the kinematic domain, you have these 3 components of the Landau variety where the singularities sit. Okay. So I think I want to stop here with this lecture, and then in the next lecture I will say a couple words about how this how to compute this in more interesting cases. Okay. All right, so this is now the final lecture of this very short series. So last time we looked at this bubble integral with two masses and a momentum, and we looked at the what happens when the masses and momenta change and the points move around. And we noticed that there's usually you can deform the contour and avoid a problem, but there are these situations of a pinch at the end, or an endpoint singularity, or a pinch of the integration contour between two singularities that you can't avoid, and these cause the singularities of the function. And then we define the notion of the Lambda variety, which is just this object, this subspace where the singularities sit. And in this case, it has three components. It's given by three polynomials in terms of the masses and momenta. And we do a little picture. But now let's look at what is actually happening when you go around these singularities. So how does the function change, and where does the multi-valuedness come from? So yeah, so let me just take all this away. So let's think about a analytic continuation now in these kinematic variables. Analytic continuation and monodromy. So this is different, right? But what did we do for the dimension and the indices, right? We used integration by parts and changed the integrand, but the integration domain was always the same. So here we've already seen that we have to deform the integration domain to do the analytic continuation. So it's a very different business. So let's do the following. Consider a small loop in M1 squared around 0. Right, so you think of your coordinate M1 squared, right? You know that in this plane there is a singularity at 0. As we discussed earlier, when M1 squared is 0, there's a singularity of the function. But if you view M1 squared as a complex variable, right, you can go around 0, right? So whatever your value of M1 squared is, probably somewhere on the positive real axis, right? Then you can take it there, make it complex, and run around 0. So this whole business really uses the complex structure of everything. So we need this freedom of the complex plane to get around singularities and talk about monodromies. So now we start with a real M1 squared, and we make it complex, go around the singularity, and come back to the initial value of M1 squared. And the question is, what happens to the integral? So if you think a bit about what happens to the function, so if so when we think of M1 squared absolute value very small, then you can check that one of the singularities, there's one of them that goes to 1, right? This because we realize this vanishes exactly when one of the zeros of the f polynomial goes to 1. So there must be a solution that is close to 1. And indeed, if you work it out in first approximation, if I didn't make a mistake, it looks something like this. So near this endpoint singularity, indeed one of the zeros is close to 1. And when M1 makes a tour around 0, then also this S2 makes a tour around 1, right? So you have this endpoint of the integration path And wherever your S2 is, right, maybe for Euclidean p squared, this is positive. So maybe you start out with an S2 somewhere here. And then this S2 runs around 1. Okay, so now we have to do the contour deformation. And in this case, you can easily visualize what happens in higher dimensions. This gets extremely complicated very quickly, as you'll be able to imagine after this one. But here, everything is easy to do. So we start out with our initial integration path. And for this whole situation, I don't really care where S1 is. I mean, you could work out where S1 is exactly. It doesn't really matter. The point is S1 is somewhere. It doesn't concern us. Well, what happens is that we have this S2 that wants to go around 1. So what we have to do is we have to do a contour deformation. Yeah, I'm not sure how many stages I should draw. So we say maybe in the beginning we do something like this, so that we can move the S2 somewhere in there, right? So we came this way and have put it there. And now we go a little further from 0 to 1. Okay, so maybe we have moved it already to here. So we started here, we moved it all the way there. So essentially you're creating like a little tunnel around S2. So it's really entwining the integration path when you do this. And let me maybe do one more. We have 0, 1. Okay, so now that's the final one. So S2 is again where it started, right? It's again positive real. We've done the full tour. And then what happened to the path? And now I have to, yeah, I think it's something like that. Okay. Okay, so you figure out that if when you do this contour deformation, in the end you're computing the integral over this contour, which is not the same contour that you started with, right? So this is the whole point of this. So now when you look at the integration path, so you have this thing. Then you can deform it further and write it in the following form. So you can also say, okay, you go this way, right? So you can also say, well, let's first go to 1 and then out of 1 again and then around. So I hope you see what I mean. You go first to 1, then you make a sharp turn, you go down, and then you do this loop. Yeah. So in a sense, what you want to say is that this is the same as doing the straight line, and then you do also a loop. And if you want to make this equation precise, this is something in homology. In this case, you could also talk about the fundamental group. But there is a mathematical statement to make these kind of a mathematical setup to make these equations precise. But in this case, it's enough to just know your path integrals. I mean, integrals along a path from complex analysis. So the point is that the integral now over this deformed path of our integrand dx over f is the same because it's a path integral. You can stop at any point. So we can stop at this point first and then add the integral over the rest. So you can write it as the integral over the straight path plus the integral, which is now an integral over a closed curve, this. Now this, of course, this is just the original integral. And this here is an extra term. So what happens, you do the analytic continuation, you're back to the same values of m1 squared. And you almost get the same function, but you get a little extra term. And in this particular case, because it's an integral over a closed circle over around a pole, right, by the residue theorem, you know, actually this is, you can express this. So this in general, this addition, the difference between the continued integral and the original integral, this is called the monodromy, or rather the variation. Or the discontinuity. And in this particular case, you know, it's something like 2 pi I times the residue at S1 dx over f. Okay, so the bottom line of this little picture here is that, okay, so indeed we are multi-valued, right? So because you've seen you can give two different values to this Feynman integral for the same values of m1 squared and the other data. And if you do analytic continuation, you change. You add certain multiples of this discontinuity. So we have multi-valuedness. And the second observation is that the variations are computed by integrals over deformed contours. Deformed, or simply just different contours. And this generalizes, so this was a one-dimensional picture where things are very easy. But this generalizes, so there's this, there's a theory called Picard-Lefschetz theory. And there are things called vanishing cycles. So maybe you've heard this. So mathematical works on these monodromies, these vanishing cycles show up all the time. So there is a theory that explains how to do this in principle, in general, but as I said, it's very complicated. And there's lots of subtleties. And there are some cases, some variations can be computed by Cauchy rules. So in case you have come across this, this is a special case of this setup. But I don't have time to go into more detail. In the remaining time, I just want to give a sketch of how you can at least compute the Lambda varieties, like the location of the singularities of more complicated integrals. Whereas if you really want to compute these monodromies in general, it's a very complicated business. It's also very tricky. You have to make really sure you get all the signs right and everything. So I will take the easy route, and I will only look at the location of the singularities in the final part. So maybe just as a reminder, the first, what was this Lambda variety? It was this location of singularities of the integral. And in the example we did, this was the first step, right? So after this analysis, the insight was we have these singularities. And knowing the singularities can be pretty useful. If you know the singularities, this can be helpful for differential equations. Also, when you do manipulations with polylogarithms or the symbol and things like that, knowing the singularities, or sometimes this is also called the alphabet, is very useful. So I just want to say some words about how can you compute these singularities. So, and computing them exactly is tricky, but at least you can get some good idea of what's around. Computing Lambda varieties in higher dimension. So there is an approach to do it. I mean, you can define what the Lambda variety is in general, but then it's extremely complicated to compute it. There's also a setup in momentum space. So, I mean, the actual Landau equations, maybe I should write this down. So there's Landau equations in momentum. Well, actually, it's a mixed representation. You use momentum and Schwinger parameters. So this is something you can find in the textbooks. But for these lectures, I want to stay with the parametric representation. So here, use parametric integral representation. So I won't have any loop momenta around. And the idea is to do a recursion step by step, one variable at a time. So we repeat the one-dimensional analysis step by step for each integration variable. So for each Schwinger parameter. So this means we have a lot of intermediate stages and intermediate Landau varieties. So we start with Landau variety of the integrand. And this we can easily write down. What is this? So let me call this just S. Yeah. Where we know that the integrand is a rational function and the denominators are only u and f, right? So in the beginning, we know that these are the only singularities. In our bubble example, we didn't have u, we only had f, right? So sometimes it's enough to only start with f or u. But in general, you may have both of them as a start. And now we want to integrate, or at least think about the singularities after integrating one variable at a time. So how do we do this? So definition. So let's suppose we're given a set of polynomials. Of a variable or of several variables, but then you just assume all the other variables are fixed for the moment. And then we do the following things. It's a list of several objects we have to look at. So the first thing is to look at the values of the polynomials at 0. Right? So I assume that these polynomials are irreducible. And so in general, 0 is not going to be a 0. But the constant coefficient, right? So this is the constant coefficient. we keep track of those. Right, so what is the idea behind this? Well, this is an endpoint singularity. At x equal to 0. Right, so if your integrand has a 0 at x equals 0, this is an endpoint singularity. So fi equals 0 is the location of singularities. So if you're suddenly in a configuration where one of your zeros is an endpoint, just as we saw in the bubble example, this is a cause of a potential cause for a singularity. Okay. So similarly, we take the leading coefficient. And this corresponds to endpoint singularities when x goes to infinity. So in the bubble example, I used the delta function to write things as integrals from 0 to 1, just to remove some potential for confusion. But often you can also use the delta function to set the variable to 1, and then all the other variables are integrated from 0 to infinity. And when you think a bit about what happens at infinity, then indeed, when the leading coefficient suddenly becomes 0, this means that at infinity, the scaling of the polynomial changes, and this can create a divergence at the infinity endpoint. So these are taking care of the endpoint singularities. And then we have all sorts of pinches. And the pinches come in two types. So there are the discriminants of the polynomials. Right, so this is pinch between two zeros of this polynomial fi. Right, so we had a case where f was quadratic and two of the zeros of f did pinch the path. But in general, we have several polynomials. So it could also happen that maybe a zero of u becomes equal to a zero of f. So this would also be a pinch. So this is what's missing in what we've done so far. And these are called resultants. So these things are called resultants. And I give an example in a second. So these keep track of pinches between zeros of f, or between a zero of fi and a zero of fj. And again, I'll give an example for this. Or let's do it right now. Example. So if fi is linear, ax plus b, right? Then this resultant fi fj is just a to the degree of fj times fj evaluated at the zero of fi minus b over a, right? So what is the idea here, right? You're looking for situations where the fi and the fj share a zero. They have a common zero. In general, they don't, but you're looking for the configurations where they suddenly do share a zero. So if fi is linear, then you know the zero is always minus b over a. So it has a common zero with fj precisely when fj evaluated at the zero of fi is 0. Right? So this is what you do. This factor here is only to cancel all of these denominators a that you get by plugging this in, so that you get a neat polynomial. So this is really not important. You're just plugging in this 0 in fj. Yeah. And there's generalizations of this when none of the polynomials are linear. You can always write these down. Okay, so we've defined the list of all of these things here. And now what was the definition? We denote this as lower script x, the irreducible factors of all of these things above here. So I hope it's somehow clear where this comes from and why this makes sense. And I'll give an example at the end. Just the statement of the result. So we have defined these sets of polynomials. Then the result is if you have an integral, the Lambda variety of the integral, the Feynman integral, say, is a subset of these iterated reductions. So you start with U and F, and then you reduce out the first variable, and then you do it with the next variable, and so on. Okay, so what is the idea, right? This thing here, these are the singularities when you've done only the integral over x1. Yeah, so if you only integrate out x1, this is, I explained, this is precisely the Lambda analysis. We take all the pinches and all the endpoints. So when you integrate out the first variable, this is still a function of the remaining variables. And as a function of the remaining variables, these polynomials give you the singularities. And now you just start again. So you have a function of x2. After you integrate x1, you still have a function of x2. You know where its singularities are. You just computed those. And then you compute, okay, what are the singularities after also integrating x2? So you keep doing this. And this is why in the end, you know that the singularities of the final result are certainly contained in what you computed. So finally, let me do an example. So now we want to have at least two integrations to see something interesting. So I'll take the triangle integral from earlier. So we have three momenta, P1, P2, P3. And we have the three edges, 1, 2, 3. And this triangle integral I want to look at in 4 dimensions with the indices equal to 1, no masses. And I use the projective delta distribution to fix x3. The graph polynomials, we looked at them at the beginning of the last lecture. So now I set x3 to 1, right? So I had to set x1 plus x2 plus 1. And the second polynomial has the 3 momenta in it. P3 squared x1 x2 plus p2 squared x1 plus p1 squared x2. Okay. And now we start with the Lambda variety of the integrand. Well, what is actually the integrand? Well, the integral, if you work it out, the superficial degree of convergence is 1. So the integral representation actually is, it's a double integral. Dx1, dx2, uf. Right. So indeed, for this triangle integral in 4 dimensions, you have both polynomials, u and f. So really have to start with both of them. So you take s being x1 plus x2 plus 1. And you have the other component where, let me write it again here, the F polynomial. So these are the singularities of the integrand. Now, the first step is the reduction, the first variable. So what do we get? So for each component, for each defining polynomial, we take the constant parts, the leading parts, and we take discriminants, and we take resultants. So constant part with respect to x1, right? So if you put x1 to 0, you get x2 plus 1 here. And here, when we put x1 to 0, we get p1 squared x2. Leading coefficient. Well, here the coefficient of x1 is just 1. And here the coefficient of x1 is p3 squared x2 plus p2 squared. Then we have the discriminants. So remember, this is looking at where we have repeated zeros. But actually, both polynomials are linear in x1. So they only have a single simple zero. There's never a repeated zero. So there are no discriminants here. That's because u and f are linear in x1, right? And then we have a resultant. So how does this go? Now we have two linear polynomials, right? And we're looking for a common solution to both of them, right? So when you view these as linear equations, you can actually write this condition as a determinant, vanishing determinant of the coefficients. So when you plug in the 0 here, right, the 0 here is -1 minus x2, right? So the resultant is equal to f at x1 equal to minus x2 minus 1. So yeah, you plug this in, right? You see what you get. So it's something like p3 squared x2 plus p2 squared. You plug in x1 being x2 plus 1. I just changed the sign here. Minus p1 squared x2. Okay, so this is a polynomial. Let me call it delta. Okay. And this is it, right? We've done everything. So whenever any of these vanishes, this is a potential singularity for the function you get after integrating out x1. So, but now look at this, right? This is 1. I mean, 1 never vanishes, right? So this is, we can forget about this one. And here we have a product of two things, right? So this is 0 exactly when x2 is 0 or when p1 squared is 0. So this is what I mean by irreducible factors. So in the definition, I said we take the irreducible factors of everything. So I would split up this product p1 squared and x2 just in its individual factors. Okay, this really doesn't matter much. It's just like to have a more tidy bookkeeping of everything. So then the result is okay after this first reduction, this sx1. So now this has components now that only depend on x2 and the kinematics. So there's a component like there's x2 equals 0. There is a component p1 squared equals 0. So this comes from here. There is a component x2 plus 1 equals 0. From there, there's this component p3 squared x2 plus p2 squared. And then we have this discriminant. Sorry, the resultant. We have this resultant. Okay. So just to remind you, what is the meaning of the set? These. So these are the singularities of the function, let me call this I1, which still depends on x2 and the kinematics, which is, as I said, which is after you integrate out the first variable. Right. So it still depends on x2. So in a sense, this is itself a Lambda variety. This set is the Lambda variety of this integral. Okay. Now we're almost done. We only have to do one more step. Next step. Reduce x2, and we use the same rules. So we look for constant parts. Okay, so what happens when you set x to 0, right? I mean, this polynomial has no constant part, so there's nothing from here. Okay, we still have p1 squared, right? I mean, that's the constant part of this polynomial. Here there's a constant part 1, but as I said earlier, 1 doesn't really matter. 1 is never 0, right? So this doesn't give a singularity. Here we have a constant part p2 squared. And I don't think there's an interesting constant part in the discriminant. Yeah, I think it's again a p2 squared. Okay, then we look at leading coefficients. Well, nothing interesting really here. There's another one. Then we have p3 squared. Okay. And the leading coefficient of the resultant is, this is quadratic, right? It's also p3 squared. So we don't get anything new. Okay. Then we have discriminants. And indeed, in discriminants, you get something now because there is a quadratic polynomial, right? This resultant from the previous step, this is quadratic. So this now can have a pinch between its two zeros. So there's a resultant, a discriminant of this thing. So there's some d delta. And if you work out what this is, this looks something like this. So you can use the same ABC formula again for any quadratic. And in this case, it looks like this. So it's actually very similar to what we saw for the bubble, just that the role of some of the masses is now played by some other momenta. So it's some quadratic expression, also known as a Klein function of the external momenta. And finally, we have to look at resultants, right? So we have to look at when do we have common zeros between any two of these, right? I mean, we've already taken care of all the zeros, common zeros between x2 equals 0, right? These were the constant parts. So those are all done. Now, if we put x2 plus 1 and this polynomial, they can have a common 0, right? So if we put x2 equal minus 1 and this one, so we get something here that looks like p3 squared minus p2 squared. So this is a funny looking singularity. And then you can check that if you look at common zeros of any of these with a resultant, actually you don't get anything new. It's clear, right? If you have a common zero of x2 plus 1 with this thing, well, then you can forget about this part because it's already 0. So it's actually just a common zero of this one with this one. And that means x2 equals 0, which you already have. So you can check there is nothing interesting otherwise. Okay, so we're done. So we just take all of these factors, and then the conclusion is, okay, this double reduction, which contains the Lambda variety, this was the theorem, has 5 components. So we have p1 squared equals 0. We have p2 squared equals 0. We have p3 squared equals 0. We have this discriminant equals 0. And then we have this funny little extra component, potential singularity, when p3 squared equals p2 squared. Okay. So I hope this somehow clarifies what this procedure is. So this whole thing is called polynomial reduction, right? Because you're working with sets of polynomials, and at each step you reduce a variable. So at each step you reduce out a number of variables, and you get a bigger number of polynomials. Normally, anyway, so this is called polynomial reduction, and this procedure was introduced by Francis Brown in a paper on Feynman integrals that you can find on the archive. And so it's a different approach. I mean, you can also do this Lambda analysis in momentum space or in mixed representations. One nice feature of this thing is that you can easily automate this on a computer if you have a software that is good with polynomials and factorizing polynomials. This can be easily programmed. And so you can get a handle on the singularities. Now, there's obviously something that bothers you about this. If you have some experience with Feynman integrals, you would see there's no reason why at p3 squared equals p2 squared there should be a singularity. So actually it turns out that this is spurious, right? Because the theorem only tells you that the lambda variety is a subset of those. So you know that these are the only singularities that could possibly appear, but it doesn't mean that actually every integral is really singular at all of these points. So this one here is spurious. So as an exercise, you can say, okay, exercise, do the reductions in reverse order, right? So you first reduce x2 and then you reduce x1. And then you will see that this thing does not contain this extra component. So from this you conclude, okay, well, the lambda variety, you're always computing the same integral, so you know you can actually intersect over both directions. If you first integrate x1 and then x2, or you first integrate x2 and then x1, you're still computing the same integral. So if this is an upper bound on the singularities, and this is also an upper bound on the singularities, you can intersect them. So if you do it in two different orders, you can quite often get rid of a lot of spurious terms. And now this intersection is really only the 4 parts that you want that are actually there. So you can actually show that these 4 remaining pieces, that indeed you can find integrals of the triangle that are singular on these. So this is the actual, this is actually equal to the lambda variety. I think I'm basically at the end of the time that I have. So yeah, I hope you enjoyed the lectures. If you have any feedback or anything, I'm happy. Please do let me know. If you find any typos, do let me know. The thing that I've written, these pages, they will be scanned and they should be available to you on the website of the school. And then there will be an exercise sheet, which hopefully is exercises that make some of these things a bit more understandable. All right, thanks very much, and enjoy the school.